applications. Yeah, let me accept this. All right. So we're gonna talk about physics and neural networks. So at the second part of my talk, we're gonna go a little bit deep on beams for uncertainty quantification, and in the context of high-dimensional uncertainties in particular. But I'm gonna motivate the need for this research using an example from extraterrestrial habitats and the challenges that we face while we're trying to design them. Now, before I even start with that, so that you know where I'm coming from and what it is we're doing, I'm going to give you a quick overview of what we do in my lab. And so the lab is called Predictive Science Laboratory. This is the people who do all the work, my graduate students and postdocs. And if you want to hire people who are familiar at the same time with machine learning and engineering problems or physics based modeling and so on, people who basically can touch upon both fields, data science and physical modeling of mechanical systems and beyond. This is a good pool to start with. So let me know if you're looking for people. Several of these will be graduating next year. So the mission of my group is to create artificial intelligence to accelerate the pace of engineering innovation. So basically, how can we replace what human engineers do in terms of analyzing their systems, running, setting up and running simulations by hand, feeding data, trying to calibrate models and all that, designing components for systems or systems. How can we, or discovering faults in systems, how can we accelerate all that? How can we do basically what engineers do without the engineers? You understand later in my talk why we need that. I'm going to reiterate on that a couple of times. If we want to, you want to go to Mars and build a habitat there or a research base, you're going to have to leave it on its own for quite a bit of time. So, and the data link, the connection with Earth is very, very slow, and there's a huge delay. So it's next to impossible to control the habitat from the Earth. The habitat will have to be autonomous in some way. So the philosophy in our group is basically these, it stems from these four things. That's probability. I'm religiously Bayesian. I think probability is a language you should use to describe uncertainties. But at the same time, standard machine learning is not sufficient to do what we need to do with engineering systems. We cannot extrapolate with classical statistical learning. We need to infuse our models with physical knowledge, or essentially capture causality inside our models. And in addition to these three basic pillars, so probability, physics, and modern machine learning, which I mostly use to represent functions, I try to get away from solving toy problems, even though today I'm gonna end up solving a toy problem at the very end. Because this is what I have been doing all my life as a researcher, and now I'm trying to get into real applications and to the point where I cannot actually solve the problems. So my group is gradually steering into more and more realistic settings. Just to give you a glimpse of some of the current applications. So one is on combustion engines and digital twins of combustion engines funded by Cummins, which is the world's biggest manufacturer of combustion engines. We cannot talk about that because it's under a non-disclosure agreement. Same thing with Ford electric motors, design of electric motors. And with Eli Lilly, a pharmaceutical company, we work on designing injectors, auto injectors, basically machines that allow you to inject drugs on your own. And the other big application that I have is high performance buildings. So this has been going on for about 7 years. We have done quite a bit of work there. But what is the dearest in my heart right now is resilient extraterrestrial habitats. And it's one of the two things that I can actually talk about because it's not restricted. So that's what I'm going to talk about. All right, so the overarching research themes in my group are as follows: high dimensional uncertainty quantification. So you have physical system, you want to propagate uncertainties through it, but it's not 1 or 2 or 5. It's a huge number of random variables that you want to pass through. Sequential design of experiments. If you can afford a certain number of experiments or simulations, which one should you do so that you reach your objective under your budget? Physics informed machine learning. How do you put physical knowledge inside machine learning? It's crucial for extrapolating. Discovery of causal mechanisms from data. This is essential for the NASA project because it lies in the heart of detecting unanticipated faults. We'll talk about this in a while. And then I also do a little bit of modeling of humans as a disturbance to engineered systems. This is in the context of high performance buildings and also extraterrestrial habitats, and also modeling humans as decision makers inside an engineered system. So imagine a human interacting with the mechanical devices of a smart building, or an astronaut or a researcher on a Mars base that interacts with the base. All right, so let's dive a little bit deeper on extraterrestrial habitats and see some of the challenges we have there. So the Resilient Extraterrestrial Habitats Institute it's a huge endeavor led by Purdue, and we have University of Connecticut and Harvard participating with us, as well as and University of Texas San Antonio, and we also have a couple of industry partners. And our goal is not to design an extraterrestrial habitat. Our goal is to create the infrastructure that you need in order to design an extraterrestrial habitat. So the big challenge is that you're on Earth, you're not on Mars, so you cannot have the environment on Mars. So you cannot do experiments as if you were on Mars. So the question is, what do you do? How can you create an experimental facility that allows you to design stuff that will operate on Mars while you're on Earth? And the difficult thing here is that it's not like building something on Earth. You can build something on Earth 1,000 times. We have been building things for thousands of years, if not hundreds of thousands of years, and we kind of know what works and what doesn't work. When you send something on Mars where you're going to put people in, you're going to have to do it once and do it right. So you don't have the luxury of failing. So this is a big question. How do you evaluate the performance of these space technologies on Earth? That's our question. And to do that, we do three things. So first, we make models of everything: the external conditions, radiation, dust on the atmosphere, if there is atmosphere on that space, moonquakes or Marsquakes, temperature fluctuations, and so on and so forth. And also, we model all the mechanical systems and the structural components of the habitat, everything from the thermal management, the pressure control, to the oxygen generator, to the waste processing plant, power generation, solar panels, nuclear generators. Everything is modeled using physics-based models as realistically as possible. So that's what I call here the MCDT. I'm not going to bother you with what it actually means. But of course, this is just modeling. It's not sufficient. Some things we cannot model very precisely. So then we go into cyber-physical testbeds. So basically, we separate the habitat into a simulated part and into a real part. The structure, for example, is real. The thermal management system is going to be real. The robots that are fixing things in our habitat are going to be semi-real. And the idea is that you have now a system that you can basically experimentally test whatever is working well on Earth, and then simulate everything that you cannot have, right? That's the idea. And as part of this project, now we are on year 2. As we're going through year 3, 4, and 5, we're actually going to make a replica of a habitat at Purdue. And I'm leading the awareness thrust, which is about a third of the institute. I'll tell you what is the awareness thrust, but on the back, on the code of the awareness thrust is a model of a habitat of a coarser nature, something that you could query many, many times and run counterfactuals on it very quickly so that you can plan. All right, so what is situational awareness? So it's answering two questions. First, where are we now? Where is the habitat now? Questions like, are the ambient conditions safe, comfortable for the crew members? Is there dust on the solar panels? Is there dust on the radiators? Is there damage on the structure? The habitat is continuously being hit by meteoroids. What kind of damage? Where is the damage? This is all known as fault detection and diagnosis. So this is one part of awareness. The other question is, where are we going? Questions like, what is going to happen to the ambient conditions if we shut down the thermal management for a while? How much time will we have until we fix a structure leak? So in the International Space Habitat, for example, they had a micro leak that they had detected, which they decided to ignore for a year. And it turns out it was okay. So how do they know that it wasn't so important that they had to fix it right away? This collectively is called prognosis. So how can you predict what's going to happen to your system? All right, so how is situational awareness implemented in our case? For each one of the systems that you see here, structure, power, environmental control, interior environment, so on, we have two things. First, there are sensors measuring physical variables, temperature, pressure, acceleration. And then there's a computational component that processes the raw data to infer the underlying health state of the system. This is called the fault detection diagnostics component. Then these data go to a human or to the command and control. Part of the command and control could be a human, and the human can look at the results and make decisions, or it could go to an algorithm that is making decisions. Here's how this looks like for the structure. So you see here our structure is going to be hit by a meteoroid. And then on the right, you see the probability that a certain structure segment is healthy and how it is being detected by the system. And then at some point, we're going to start making repairs. And the system, the fault detection diagnostics, detects that the structure is now back to the nominal conditions. Now, we spent, the thing that you see here, like 10 seconds, probably spent 1.5 years making it. And on the back end, there is a reference model, which is an actual, very fine, detailed, fine element model of the habitat. The meteoroid hitting the structure is actually being modeled. There's an impact model. There's damage model. There's a damage created on the reference model. Then there is a robot going there and fixing stuff, and the action of fixing, of repairing the structure is modeled. And then on the right, you see the fault detection diagnostics, which uses another model, right? So there is this distinction between a reference model, which is the ground truth for us, and then the model used to detect the faults, which has to be different. So why is situational awareness needed? It's kind of obvious. If you want to make a resilient habitat, you need to know where you are and where you're going so that you can take corrective actions, right? So if your habitat deviates from the safe region where you want it to operate, by safe region, we mean basically the crew must be safe and comfortable, right? There's certain regions of temperature, humidity, and oxygen and pressure that you need to be inside so that people can survive. And you should also be able to carry out your scientific missions. So situational awareness is needed so that when you detect that you are deviating from this safe region, you choose controls to bring the system back. We call these safety controls. And in our case, it's implemented as follows. Basically, the command and control monitors the health state of the habitat, and it can make two types of decisions. It can change the set points, the operating set points of the system. So it can decide to shut down, for example, the thermal management. It can decide to change the temperature set point. Or it can send commands to agents, them being either robots or humans, to go and carry out maintenance and repair jobs. Now, as I told you, we try to model all that, okay? And this is the kind of, this represents 2 years of work. On the back end, they are basically all the systems of the habitat being simulated from power generation, nuclear, solar, thermal management, pressure control, and so on. The agents making repairs are simulated. The communication network that the habitat is using to send data from the sensors to a data repository is there. The data repository is there, and there is a first version of a command and control or a decision maker. It's a simple reflexive decision maker at this point that actually makes decisions. If it detects a fault, it sends an agent to fix the fault. And you see here, for example, what we have here is basically a meteoroid hitting the ground, and there is dust being raised and deposited on the solar panels and on our radiators. And that's why power production is going down by the solar panels. And then after a while, the fault detection diagnostic systems pick this up and they send the agents to fix it. All right, so this is just a case, a specific scenario that we managed to put together. Imagine there are about 40 people collaborating to make this happen. But really, we try, now that we have closed the loop, we try to make a system that will have more complexity, a system that we can simulate and things can happen stochastically. We do not have a specific scenario we're following. And something that can basically exhibit emerging behavior. Because really where we want to go is we're going to have a case study for doing research on unanticipated faults. How can you automate the discovery of unanticipated faults? That's where we're going. So perhaps in a couple of years we'll have more, but it has been extremely difficult just to put together what you saw here right now. All right, so where do physics-informed neural networks fit? So now I'm gonna, I give you the overarching picture. Now we're gonna start going deep. And at the end, we're going to actually do a mathematical proof or basically schema over it. So let's see. So there's a need for real-time physics-based fault detection diagnostics. The keyword here is real-time. All right, that's needed for fault detection. Fault detection diagnostics requires physical models, and the problem that you're solving really is a filtering and calibration problem, or in other words, a data assimilation problem. And this is notoriously hard to solve, especially in high-dimensional settings. All right, so what do you need in order to solve this problem? And by solve, I actually mean approximate the solution, not actually solve it, is surrogates of the physical models with high-dimensional inputs. So we're talking about basically solving partial differential equations, parameterized partial differential equations for all possible parameters. Because if you have these surrogates, then you can use the standard techniques for solving the filtering problem. You can do particle filters, you can do variational inference, and so on and so forth. All right. So let's go to today's talk, today's technical part of the talk, which is about solving stochastic partial differential equations using physics-informed neural networks. So I have done quite a bit of work on this. In my group, we tend to go a little bit slowly when we publish things. I try to do an almost exhaustive study of things. So imagine this paper, we started it perhaps in 2018, Actually, no, perhaps this is when we started. It took us 2 years to get it published because things did not work, and we wanted to know why they didn't work. And I'll explain in my talk why. The very first paper we did on neural networks for high dimensional set quantification was this, called the DPUQ by Rohit Tripathi. And as a spin-off of that, Rohit basically developed the deep active subspaces, which is what Uder found and called me to talk here today. And it all started really with a paper we wrote on Gaussian processes with built-in dimensionality reduction. It's basically active subspaces coupled with Gaussian processes and using maximum likelihood to find the active subspace. So all these papers use the active subspace structure for the network. So in the top 3 papers, we have a neural network that funnels into a low-dimensional code, let's say, and then opens up to the solution. All right, so here's what we want to do. We have a prototypical stochastic partial differential equation. It's an elliptic partial differential equation. It's this could be an equation from heat transfer, flow through porous media, or magnetostatics. As a matter of fact, the same equation we used before in electric machines. And A is there, the magnetic vector potential. So this A of X here is not, you can think of it as the conductivity or the permeability of the ground or the magnetic permeability. And this A of X is now a parameter. And it's not a simple parameter, it's a function. It's a function that can vary. Why it can vary? Depends on the application really, but it could represent manufacturing uncertainty, or it could represent, if you're looking at flow through porous media, for example, it could represent the fact that you don't know exactly how the ground looks like. If you pump drugs into the body of a human, it could represent how the tissue looks like, which is something that you also don't know unless you cut it up and look at it. But then for new tissue, you will still not know how it looks like. It's a prototypical example that I would like to be able to solve. And what we want to do is we want to solve this PDE, this boundary value problem, for all possible A's. Okay, so A is an image. You should be able to change the image to something else and get the solution almost immediately. That's what we want to do. And we're not going to follow the common approach of taking the A represented with a Gaussian random field, do dimensionality reduction on the random field, using carbon expansion, and then getting 50 or 100 random variables and solving the stochastic PDE for them. We honestly are going to try to do it using the pictures. So that's the kind of network we want to build. We want to build a network that takes a special position in an entire picture and spits out, let's say, the temperature at that position if the heat transfer coefficient or the thermal conductivity, or whatever you want to call it, is represented by that picture. That's what we want to do. We want to build this monster. Okay, so what is the common approach? That you would use if you read one of the, let's call them classic papers on physics-informed machine learning. By the way, I'm assuming that you have seen physics-informed machine learning at some point, presented either by George Kaniadakis or Perikaris or Mazia Aresi. So I'm not going to go through the details, but you'll get the idea here. Basically, you represent the solution of a parameterized PDE using a neural network, and you try to make a loss function that incorporates the PDE inside it, and by minimizing it, you're solving the PDE for all parameters. That's the idea. So the classic way to building this loss function, the physics-informed loss function, let's call it that, is to take the PDE, move all the terms to one side, square the terms, and then you integrate over space and time, and you take an expectation over all the random parameters you may have. And in the end, you get something like this. So this is basically inside all the integrals, you have the residual, square residual of the PDE, and you integrate over space. This gives you a function of xi, because xi are the parameters. Then you integrate over the parameters and you get a number. Now, if you manage to bring this exactly to 0, you have solved the PDE. You have found a neural network that solves the PDE for all parameters. Okay, there's only one problem. If you try it, it's not going to work. Okay, and it took us about a year to figure out that no matter what we did, it wouldn't work, especially in high dimensional settings. By the way, it works if xi is 2, 3, 4, 5 dimensions. It works. There is a paper by NVIDIA where they do this they follow the same approach to solve heat transfer coupled with Navier-Stokes for the heat sink, where the geometry is parameterized by 5 parameters. So in low dimensional settings, it works. In high dimensional settings, it does not work. And the reason is that there are multiple local minima to this loss function. And every time you run your stochastic gradient descent, you get a different one. That's the problem. All right, so whenever things do not work, you need to step back and do a little bit of theory, introduce your probability space, sigma algebras and all, and study the generic problem and hope for the best. So in this particular case, we looked at the generically elliptic partial differential equation that almost surely satisfies Dirichlet and Neumann conditions like that. And you see here that omega here is the essentially represents uncertainty. So we allow here for everything to be uncertain. A is thermal transfer coefficient, C, F, source term could be uncertain, the Dirichlet boundary could be uncertain, the Neumann boundary or natural boundary could be uncertain. And the question is, can you come up with a loss function, the minimization of which solves this PDE provably, in the sense that ideally you want this loss function to have a unique solution. And in this particular case, for this particular PDE, it is possible. And it's easy to take a classical theorem for elliptic PDEs and generalize it in this setting. You have to assume that the heat transfer coefficients are elliptic, almost surely some constraint on C. And then within a specific space, this Sobolev space right here, this scripted U, this functional that you see right here, which you can think as the energy stored in the field, but it's not exactly the energy because now there's an expectation over the stochastic part, the stochastic part, this outer expectation. If you just had the internal integral and no parameters, it would be the energy. Once you integrate over all parameters, it's not the energy anymore, but it kind of looks like an energy. So if you try to minimize this loss function, you will get a unique solution in this particular Sobolev space. There is a unique solution. And here's a sketch of the proof. I'm just gonna skim through it. I'm not gonna explain anything, but if you want to know more, you can ask me. The proof is straightforward, really. You just generalize the proof without the parameter. You just need to be a little bit careful with things with the concepts you're using. So you take you saw that the variational problem has a unique solution first. You take the first variation with respect to a test function. You show that the linear form you get is coercive. You apply the Lax-Milgram theorem, and that's it. Okay, that's basically the proof. And then to prove that the solution of the variational problem solves the weak form of the PDEs almost surely, you pick some test functions, you blank them in the linear forms, you use the fact that the stochastic part of the test function is arbitrary to get the weak form almost surely. So it's very, very straightforward to go over it. All right, so we have now a loss function that has a unique solution. This is great, but we now need to develop a practical algorithm for minimizing it within a specific space of functions. So the first thing we're going to do is we're going to make the representation of the uncertainty finite dimensional. Okay, you cannot work directly with omega. Omega is abstract here in any way. Now, if you have fields, you have to discretize them if you were to follow our approach. Now, if you don't like discretizing fields just like that, we're going to discretize fields with images, and you're worried about what sort of error you're getting, you should look at the recent work by Andrew Stewart from Caltech, and also George Kanyadakis, Lulu, it's his postdoc on deep nets. That's too advanced mathematics for me. I'm not worried so much about it. I just discretize and hope for the best. And at the end of the day, in practical applications, you don't have the fields, you just have the pictures. So it's okay for practical purposes. Now, the other thing that we're going to do is we're going to enforce the Dirichlet boundary conditions by hand. The natural boundary conditions are inside the loss function, so you don't have to worry about them. And we're going to construct a stochastic gradient descent algorithm that converges. So let's go over these steps one by one. So here I'm taking, this is the generic form of the problem, and we're going to replace it with a problem where we have discretized things, and the way we're going to discretize things is basically treat this A of X as a picture. Okay, so the psi, which is the finite dimensional version of a representation of our randomness, is basically the value of A on a bunch of pixels. And we have about 1,000 pixels. Okay, the other thing that we're going to do is we're going to enforce the Dirichlet boundary conditions, and we do that by parameterizing the solution like this. This is a very common trick in PDEs. So you see, U is some part that doesn't depend on the parameters, B of X, and this part satisfies the Dirichlet boundary conditions, and you're going to have to make it, and it's fairly straightforward to make it. Sometimes you can guess it, but even if you have arbitrary geometries, you can still make it. And K of X is something that is 0 on the boundary, so that when you are on the boundary, B is active. When you're not on the boundary, we pay attention to this part right here, which we're going to make a neural network. Okay. Of course, this is not our idea. This is very, very commonly used in PDEs. Okay, so now we have discretized the stochastic part. We have parameterized U, and now we have to solve this minimization problem. And we're going to solve it by stochastic gradient descent. So remember that J is basically this functional of U. And when we discretized everything on parameterized U, we turned it into a function of theta, where theta are the parameters of the neural network. All right, so the key idea here, and the thing that is sometimes runs through in the literature and not explained early, is that you need to work a little bit carefully when you want to construct a stochastic optimization algorithm for this. And the key here is to turn every integral you have into an expectation over some random variables. And in doing so, you have to introduce some normalization constants. You have to do it carefully. And so it will look like that. So we replace J with a J hat. So J hat is some noisy version of J that we have constructed by using random variables. In this particular case, it looks like this. It's not that complicated. basically you can read it from the expression above, from the integrals, where we have introduced collocation points to do the integrals. And these collocation points are random and they have to satisfy certain properties. So these x's, for example, are sampled inside the special domain and they have to be identically distributed and they have to be uniform. The xi's are the pictures of the thermal conductivity and they have to be identically distributed from whatever is the process that is giving you these pictures. And of course, you have to sample the boundary. Now, if you do it like that, and you do pay attention to turning all the integrals into expectations, then you can prove that your stochastic gradient descent will converge. Okay, and it will converge no matter how many collocation points you use. You can use one collocation point, it will converge. Of course, it will converge in the limit of infinite iterations, so in practice, it may never converge. But at least you have a theoretical result that is telling you that so this particular scheme will go to a local minimum. Unfortunately, that's a guarantee of Robert's moral, local minimum, non-global minimum of the loss function you are minimizing. The common practice is to fix the collocation points, not make them random at every iteration. If you fix them, you may not converge. You actually will not converge in this particular setting where you have very high dimensional size. And that's what took us a while to figure out how to do. All right, so now let's put everything together and look at an example. This is the problem we have. This is the kind of pictures we have. This is the thing we want to build. We build it by minimizing the loss function. Now I'm going to start by showing you a comparison. Actually, let's start with this. I'm going to go back. So what you see here is on the left, on the very left, you see the input, which is a picture. In the middle, you see the prediction by finite volumes. And on the right-hand side, you see the prediction of the neural network. Now, the neural network hasn't seen any of these images. These images are randomly generated. And pay attention that the input can be vastly different. So the first, in the first row, you see a sample from a Gaussian random field with a very fine length scale. In the second row, you see a Gaussian random field with a bigger length scale. And or you can fit channelized permeabilities or thermal conductivities, which are not even Gaussian. Or what you see in the second, and this is what you see in the top row. In the bottom row, you see an input that is coming from a wrapped Gaussian process. A Gaussian process sample passed through another function. And the network still predicts well. Now, pay attention, of course, that the neural network solution is missing some of the high frequency features, right? So if you pay a close attention to the fine details of the prediction, they're missed. Back in 2020, we didn't know why. I mean, whatever we did, no matter how much time we ran we trained our neural network, how many iterations we did, we could never get these fine features in such high dimensional settings. The network tended to smooth things over. We didn't know why this was happening. Now we kind of know why it's happening. It's a phenomenon called the spectral bias of neural networks. And you can partially remedy this by introducing some Fourier features at the very beginning, especially for the special variation. All right, now let me show you some comparison with the standard way of doing things, which is with the integrated square residual. So the yellow thing here, the yellow box plots are the relative error you get in the solution of the stochastic PDE using the integrated square residual. And the green box plots corresponds to the relative area you're getting for the energy loss that we proposed in this paper. On the x-axis, you have Gaussian random fields of decreasing length scale. So the problem becomes more and more difficult as you go towards the right. It's easier to capture large length scales. It's less easy or much harder to capture very small length scales. Now you see the remarkable thing here is that the energy functional gives you systematically about an order of magnitude smaller error, and and not only that, the uncertainty here corresponds to different random starts of the training algorithm. You see that the energy functional systematically gives you smaller variance in your error. And this is indicative of the fact that the green loss function has a unique minimum, and the orange loss function, we don't even know how it behaves. Right, so that's evidence that a little bit of theory can go a long way. Right, and you can also show some that the network can actually work for all kinds of random fields. So you can train a network for all random fields that you like at the same time and have good performance, acceptable performance overall. You can show that the network is actually not memorizing things, but it's learning more or less how to solve the PDE. Because what we did here is we trained the network with a Gaussian random field. We actually trained it with a Gaussian random field that is in the middle, the one with the smallest error. And then we tried it on other random fields that it has never seen, like a Gaussian random field with a bigger length scale, a wrapped Gaussian random field, or the channelized permeabilities. And it guessed to some extent to a satisfactory degree. All right, so there's several remaining questions. For this particular problem and in general, for this particular problem, we proved uniqueness in the Hilbert space, but it's really, we don't know exactly what sort of result we get in the neural network space. There's certainly not a unique solution in the space of neural networks because you can permute the neurons and get another function that has exactly the same output values. So there are several theoretical questions, open theoretical questions, like is the solution unique in the DNN space if you come up with some sort of functional equivalence class? How does the solution behave as you increase the capacity of the network? Do you converge to the solution of the Sobolev space? These are all great questions to ask, but we are in a mechanical engineering department and we don't have the luxury or the capacity to answer them. But you're welcome to take them on if you wish. There are several other activities that we're doing in physics for neural networks, and we're always open to potential collaborations. We work on inverse problems a lot. All the problems you saw have in my applications are inverse problems or filtering problems. I'm particularly interested in solving inverse problems in one sort, or if you like, learning how to invert. And I'm particularly interested in learning how to go from data to the Bayesian solution of an inverse problem, that is to the posterior probability. Physics-based design optimization in high dimensions is what we do in with electric machines with Ford, and it's an open problem in particular here. When you can follow the common practice, like what NVIDIA did, build the response surface, then optimize it. Okay, works well for 6 dimensions. If you want to optimize over topologies, it doesn't seem like a good idea because a topology can only be represented with an infinite number of variables. And it looks kind of ridiculous to try to first build the response surface, then optimize. It would be better if you could come up with some loss function that at the same time honors the physics and gets you into a design that has the right performance for you. So if you could do it with one optimization, that would be better. Parsimonious DNN-based representations. Okay, so how do we do all that? What is the best way to represent the solution of a time-evolving system? So obviously you can just add time in the input, but this is not very economical in terms of parameters. Probabilistic interpretations of physics-informed neural networks. This is actually a topic that I really like to explore theoretically. I'm not gonna say more, but that there are some connections to statistical field theory and Feynman path integrals, and I'm not in a position to actually do it myself because I don't understand the mathematics yet. Non-parametric learning or effective physics from data. This is another topic that we have opened up in the Resilient Extra-Terrestrial Habitats project, because we need to somehow discover that something has happened to our habitat and what it is. If there's a change in the physical systems, in the mechanical systems, how can the autonomy detect it so that things can be repaired without the presence of humans? We're very far away from doing something like that, of course, but it's definitely an interesting challenge. All right, and this is pretty much everything I had prepared, and I'll be happy to take any questions if you have any.
All right, thank you, Ilias. If there are any questions, just maybe raise your hand or unmute. I see one hand, I think. Dan.
It was an applause, but I do have a question actually. So Ilias, thanks for this nice talk. So one thing that triggered me at the very end, and I'm wondering if you can say a little bit more about that. That's the the class of dynamical problems. So if you have time-dependent PDEs, so you mentioned something about that very briefly. Can you say a bit more about that?
Yeah. So we are basically in the third bullet point. So if you have a time-dependent problem, you could follow this approach, right? You represent the solution with a neural network and say, treat time just like space and the parameters. Say, okay, my neural network is now going to be a function of time as well. All right, that works to a certain extent, but if you, but your integral, right? So when you integrate, you would have to integrate over time as well, and you cannot go to infinite time. You're going to have to pick a finite time, right? So if you solve your problem by minimizing the loss function, then it's very unlikely that when that your solution will extrapolate to greater times that one you have in your loss function. Right, so you won't be able to do it within the specific time window, and that may be okay. That may be what you want, okay, but that's not what I want. I want to be able to extrapolate beyond,
sure,
beyond that time, and there is a certain structure in the solution that is enforced by causality, right? So the things that happen in the future must depend on what happened in the past. The systems are usually Markovian, right? So this is satisfied. So if you look at the map that takes your solution and moves it forward in time, it forms a group in the sense of group theory. And this is a one parameter group of transformations. The one parameter is the time. So transformation takes your solution and moves it forward by a certain amount of time. And this transformation satisfies group properties. It is a one parameter group of transformations, and it's also differentiable with respect to the parameter. So it forms a Lie. It's a Lie group. It's a one parameter group of differential transformations. So when you are in this situation, you can show that you can represent the evolution in time by the generator of that Lie algebra. So there is a mathematical object that if you manage to find it, it will tell you how to propagate things forward in time. So the idea here, and this is all all in paper right now. We haven't really done anything practical with it yet. Is that you use neural networks instead of representing the solution to represent the generator. And then once you learn the generator, you can take any fields and move them forward in time. So I would say that myself, particularly my group, we're probably 2 years away from making this something useful in terms of work.
So do you then, when you talk about solution here, there will be, I suppose I have a nonlinear PDE related to fluid dynamics. So are you then referring to the solution as the actual flow field or more in the probabilistic sense? So that you have,
It'll be,
because this sort of this group or semi-group type structure sort of holds for linear operators, I think. So I'm not sure if you can extend that to nonlinear situation.
It also works in nonlinear PDEs. It also works for nonlinear PDEs. The nonlinear PDE will have a Lie group that moves forward the solution as well. And the key here is that if you represent the solution in a parameterized way, the Lie group generator will give you a differential equation for the parameters of your representation. That's what it's going to give you. So imagine you represent your solution with a neural network at a given time, right? So temperature is a function of space at a given time.
Mm-hmm.
Then to move it for, and this has a certain number of certain parameters, say theta. Then the Lie group will give you a differential equation for the parameters, and you solve it forward using Rugi-Okuta, for example, and you move forward in time.
Okay, so it's a sort of time stepping procedure as you get that.
Mm-hmm. Mm-hmm.
Sounds interesting. All right, thanks. So is this something you're writing up, or is already out there?
No, this is one of my proposals. So this is basically me fishing collaborations. So if you're interested to know more, let me know. But
all right,
I have written down the mathematics. I haven't written down any code to test stuff. This is the stage we're at.
Okay, thanks.
All right, I think Enrico was next.
Hi. Yes, so very interesting topic and talk and very interesting list of topics. I'm myself interested in few of these, so maybe we should talk offline at some point. But so my question is, so I'm familiar, I've used myself pins for deterministic PDEs, so I'm not sure I understand the whole mechanics behind the stochastic PDEs, but I didn't understand, almost by definition, by construction, pins cannot extrapolate. So I don't understand the claim that you made that, you learn a pin for a given stochastic field, and then you can solve for a completely different stochastic field. I don't understand how that can work, because the pin is trained on that field. I mean, even just, even just for deterministic pins, you cannot extrapolate in time, for instance, right? The pin works for that domain of space and time. You cannot go further in time. So what's the catch here?
I don't know why it works to the extent that it works. I don't know why, but I can tell you what we observe. So here, you train on a Gaussian random field with these length scales, fairly small length scales, okay? And then this is the relative error. This is relative root mean square errors or relative L2 error for a Gaussian random field with a bigger length scale. Okay, so that's, you say it's a simpler problem. And then this is the error for a different random field that's not even Gaussian, and this is for the channelized field. This is how it looks like for the channelized field. So basically, you train here, you feed it this, and it predicts well, but not so well. You feed it this, and it predicts okay. You feed it this, and it predicts okay. So, okay, I say it learns how to solve the PDE, but this is in quotes. Okay, I'm not. It's not a technical claim. It's just an observation that I think it's because of the problem. It's an elliptic PDE. The operator smooth. The solution is a smooth version of the field, so it's not really that difficult. If you know what I mean, right? So there may be theoretical reasons why it works, but I don't know them. Now, if you put noise in here, it's probably not going to work, right? Or if you put something very complicated. So the answer is that learning to extrapolate in quotes, in practice, I put in a different picture and it looks okay for engineering purposes, right? Why doesn't it look complete garbage? That's something I cannot answer actually. But it's not. Remember, I trained with this random field, right? If I train with this, it cannot extrapolate. It cannot work well with a fine scale.
Mm-hmm.
So maybe it's because this has enough variability inside.
Yeah.
And again, it's not a claim that I wouldn't say this is general either. But
Okay, thanks.
as a matter of fact, if the picture was the initial conditions of a chaotic system, like a flow system with turbulence, it wouldn't work for sure.
All right, we have another question from Vignesh.
Hi, thank you so much for this talk. It's actually been quite interesting. My question's on the theoretical sort of framework that you come with the Robbins-Monroe theorem. You mentioned that in each iteration of the training sort of regime, you actually sample IID sample collocation points. So aren't you worried about when you sample each time there's some sort of covariate shift that can happen in the training data set? Because it's not just in like sets as in batches either. It's sampling and generating new sort of collocation points each time. Or is it just that the physics will take care of it within the sort of encapsulated loss function?
So theoretically speaking, if you don't sample on its iteration, your algorithm doesn't satisfy the requirements of Robbins-Monroe, and it may or may not converge. Now, the usual practice is to just have lots of collocation points and use them all the time. That's okay when you don't have parameters or if you have a few parameters. In our case, our parameters, this psi has 1,000 dimensions. So enough collocation points in 1,000 dimensions, I don't know, will be probably 1 trillion collocation points, right? So realistically speaking, I cannot have enough of them. And that's why we had to make them stochastic in practice. And it paid off actually to make stochastic also the spatial collocation points. But from my experience with pins and many and other problems, not just elliptic PDEs, the special collocation points have to be spread out enough so that you capture fine scale features of your physics. In particular, in magnetostatics, for example, where we're doing work in electric machines, the loss function is almost the derivative of the loss function is almost zero everywhere, except at the places where you have current and behind and at the air gaps. So it's basically practically zero everywhere, and only very small regions where you have a contribution. So if you sample 10 points randomly, you will hit one of these regions every 10,000 iterations. So it will converge, but it will take forever to converge. So in that case, you either have a big set of collocation points and you sample them. Either it's so big that you can ignore the error, right? Or it's dense and you sample it every time. Or you use importance sampling. So you bias the sampling so that you sample the important regions. But then you have, that's why you need to know about Robbins-Monroe theorem, because you have to get convergence, you need to go back and correct these expectations when you bias.
Right. I understand. I think there's a lot for us to talk offline. We work in sort of applying pins for a lot of magnetohydrodynamic simulations. I'll just read your papers and then I'll just reach out to you by mail if that's all right.
Just a heads up, the magnetostatics work, we're currently writing it down. So you can find it anywhere, but we can talk about it.
Yeah, the current sort of work. I've taken a screenshot of all the papers that I want to go through that you've sent across. So I'll go through that and I'll just reach out to you if that's okay.
Sounds good. Yeah, no problem.
Okay, thank you.
Okay. Someone else want to ask a question? If not, I might have one. So you mentioned you using active subspace ideas in many of your work. I'm wondering what is the main advantage of that? It's not going to lower the number of parameter or neural network weights a lot, right? And so what's the advantage of using, let's say, a deep UQ or deep active subspaces compared to using just a feed-forward neural network for the same problem?
Yes. So by feed-forward neural, you mean a network with a single layer, for example?
Yeah, or a number of layers with no deep active subspace ideas attached to it. It's like a vanilla feed-forward neural network.
Yeah. So we spent probably a year to experiment with different structures, and we have a table in the paper where we examine different structures and we evaluate their performance. So I'll tell you what we found, and then I'm gonna guess why it's working better, but I'm not sure. So we tried plain vanilla neural networks, like increasing the number of neurons, increasing the layers, like a box, for example, right? Playing with the number of neurons, playing with the number of layers. That didn't work, okay? Probably because there were too many parameters. The other thing we tried is taking the network from, it has about 1,000 inputs, and then we basically pass it through a funnel. So we take it down to, let's say, 5 dimensions or 10 dimensions, and then we open it up again, and then we bring it back again into the temperature, let's say. So we force it to go through a low dimensional representation. Now that worked better, probably because there's some inherent nonlinear active subspace or direction in the space of pictures over which most of the variability is basically expressed. Mm-hmm. And we think that by this structure, that's what is discovered. And in particular, in the elliptic PDEs, if you look at the work we did with Rohit or the work of Paul Constantine or on active subspaces, we know that for Gaussian random fields in particular, there is an active subspace that is actually linear and 1 or 2 dimensional, depending on the length scale of the Gaussian random field. So it makes sense that when you go to arbitrary fields, there's still or a set of fields, there's still an active subspace, albeit it may be higher dimensional or non-linear. Okay, so that worked well, but not perfectly. We found that adding residual connections in the network was essential for avoiding zero gradient problems. And again, you can argue that the residual connections take basically the input and put it on an intermediate layer, kind of force the network to kind of act like a correction to the identity. So like there is a simple function that you're correcting to. Yeah, but this is, I don't understand why. So there's some work done by Kaniadakis on theoretical reasons why deep neural networks are better. So he shows that it's actually better to have more layers than have more neurons. And he has some theoretical arguments, theoretical results about that for regression. And maybe he even has it for pins, but I'm not sure about if he has it for the elliptic problem. That's all I can say.
All right, perhaps one last question, and otherwise we can adjourn. I might have one more, maybe a short one. So, did you see a sharper rise in the required amount of data that you need if you get more uncertain inputs in these types of methods?
Yes, so imagine here the amount of data, if you're talking about pictures, we actually generate the pictures on the fly. So there's an infinite amount of data. So the pictures are generated on each iteration. If we run 200,000 iterations, we've seen 200,000 randomly generated pictures. So the approach is generating its own pictures from an assumed stochastic random field. And then you can feed it data from the same stochastic random field or from another stochastic random field, right? That's what I mentioned before. But I've seen some work by my former, by my PhD advisor, Professor Zabaras, on the same problem. Similar difficulty, probably use a few tens of thousands of pictures, because I think it just went with pictures. But for this problem, because it's really stochastic PDE and you can sample the parameters, right? You can generate as many observations as you want. So, but you don't solve the forward problem, okay? You don't solve the PDE. You only generate the input data. You don't have to solve the PDE because the physics are incorporated in the loss function. So it's basically an infinite amount of input data and zero output data. So, compared to the papers that you've seen on deep active subspaces, where we used input-output observations, here there are zero output observations.
Okay. Well, thanks again. It was a very nice talk. And I'm pretty sure people will contact you afterwards.
Thank you for the invitation. And yes, if you have any questions or if you want to talk about any of this stuff and particularly open questions, feel free to reach out.
All right. Thanks again. And bye, everybody.
Thank you. Bye-bye.
Thanks. Bye, everyone.